Hi, good evening, everybody. Thank you for being here, first of all. My name is Linda Bell. I'm provost and dean of the faculty. And it's really my honor to be here to introduce this annual distinguished lecture in computer science. Many of us in this room, in particular, our distinguished Professor Wright, started this program fairly recently with the help of a lot of colleagues. So first, let me just acknowledge the help of our Colombian colleagues in establishing the Barnard Computer Science program and in helping it to grow and helping it to flourish and helping to give it its distinctiveness. We are now, computer science is now one of the largest majors at Barnard. And it is also an important kind of disciplinary area, not just for majors, but also throughout the college. We have students who increasingly understand the power of computing, the power of thinking like a computer scientist, and the value of obtaining some kind of knowledge. So this program is touching so many students at Barnard. Barnard is a unique place. We are a liberal arts college, and being a liberal arts college, we have a particular way of interacting with our students, teaching our students, and thinking about the way in which information is passed on to our students. Our students are trained to think critically about major issues. And over time, and it really did take time, we've developed a kind of concept of computing for social good, which resonates with us as an institution and which is very meaningful to our faculty who are here and to our students who are here. So I just want to thank the faculty of Barnard, thank the faculty of Columbia who are here for participating. I am not going to introduce our speaker because I've been told to introduce our chair who will introduce our speaker. But since I have to leave, I do want to just warmly welcome you. Thank you for being here. Thank you for participating in this annual lecture, which is really very meaningful to all of us. And I apologize in advance that I won't be able to be here.
No worries at all. Thank you so much for inviting me.
Sure. And just a few words about Rebecca Wright, because I have them in front of me. So Rebecca, we stole Rebecca from Rutgers, where she had a very prominent career in all kinds of areas. Her research is primarily in the area of information security, including cryptography, privacy, foundations of computer security, and fault-tolerant distributed computing. She serves as an editor of the International Journal of Information and Computer Security and of the Transactions on Data Privacy. She's a member of the board of the Computing Research Association's Committee on the Status of Women in Computing Research, or the CRAW. We feel really lucky to have Rebecca here at Barnard. She's been doing a ton of things, not just for computer science, but for the college. And with that, I'll turn this over and wish you all a really vibrant talk. So thanks for having me. So
thanks, Provost Bell, including for those nice words. It's an old version of the bio. I need to update that. But the real purpose here is to introduce Professor Aarti Gupta. And we are delighted to do so. As Provost Bell mentioned, this is an annual distinguished lecture in computer science at Barnard, and so it's an exciting day for us when we hold that. Dr. Gupta joined Princeton's computer science department as a full professor in 2015. Before that, she had an extensive career at NEC Labs America, where she led a team in investigating new techniques for formal verification of software and hardware systems, contributing both to their foundations and to their successful industrial deployment. She was recognized by 3 NEC Technology Commercialization Awards during her time there. Her PhD came from Carnegie Mellon University in 1994, as well as an earlier master's degree from RPI, Rensselaer Polytechnic Institute, and a bachelor's in electrical engineering from IIT in New Delhi in India. She has served as the associate editor for Formal Methods in System Design and for the ACM Transactions on Design Automation of Electronic Systems, as well as program chair and steering committees of multiple professional conferences. And we were talking earlier today about how it's really nice to think about a talk for this kind of audience that includes everything from undergraduates to graduate students to faculty working in the very specific area, and that the kind of breadth of thinking you need to present your work that way. And so I'm super excited to hear that kind of a talk. And with that, I will thank you for being our speaker and let you go ahead and get started.
Thank you so much, Professor Wright, for your kind introduction and for inviting me. I'm delighted to be here and share with you some of the recent research results in the area of network verification. So, clicker may not work. Okay, so what I'll be focusing on in my talk today is the verification of the network control planes. And what I mean by network control planes is conceptually that part of the network that decides what routing paths to use. So here, the routers exchange messages with each other according to some protocol and according to the configurations that they have. And once the decision process is made in the control plane, then the data plane part of the network gets what are called forwarding tables, which are essentially specifications of where a given data packet that's headed, let's say, to this destination prefix can be sent out on port 1 or on port 5, and so on. So it's basically after the decision process is made in the control plane that the data plane will actually get the forwarding tables, which will determine what will actually happen at runtime when the packets that come into the routers are forwarded according to the forwarding tables. Okay. So there's a lot that's going on in a network control plane. Although the primary goal is to get traffic from point A to point B, there's security concerns about what routers should be having access to, which networks, and so on. There's also traffic engineering, depending on the load that many of the links might see, or fault tolerance to keep in mind, because it's a distributed system. Nodes may go down, links may go down, and so you have to worry about fault tolerance and about setting up backup routes. And all of this is done, including figuring out how to do this cost efficiently through programming the network in terms of configurations. So what are configurations? You can think of these as really forming a distributed program, but they are often vendor specific. So the Juniper configurations would look different from the Cisco configurations and so on. They're also at a very, very low level. You can almost think like it's a program at the assembly level. So you don't really have very many high level primitives to work with. And worst of it, as network programmers and administrators work with these network designs, they accumulate these lines of code that everybody is very unwilling to touch or change, because it's very hard to figure out manually or just by in your head what's going to happen if you change some line in the configuration. So as a result, testing or even simulation, the kind of things we do for testing software programs, can often miss buggy scenarios. And this actually happens more often than one would want. In fact, network misconfiguration is a huge, big problem. There are just so many times when the networks fail, there are outages or some security breaches, partly due to misconfigurations that are done with these networks because these configuration code are so low level and hard to reason about. So what does one do? This is not a good situation to be in. And this actually motivated the use of what's called formal verification. So let me explain what I mean by formal verification for this context. Here, what would ideally we would want is we would want a formal verifier, which would take some description of the network configurations, maybe the protocols that they're going to use. And in particular, I'm going to focus on distributed routing protocols. And for all possible forwarding tables that these configurations could lead to, you would want to consider them. You would also want to consider all kinds of packets that might come into the network, even all kinds of routing announcements that the network might be configured with or get in the future. And you want to be able to reason about all of the forwarding tables and all of the packets. And then if there is a bug, show a trace, of routers exchanging messages or of some packets going from some point to point B that violates some specification. So you want to really see a bug if the network has a violation of your correctness property in mind. And if there aren't any bugs, ideally you would want to see a proof, which would be a mathematical way of saying that the network is correct. So that's the ideal. You want a formal verifier to be able to do this. So the big question is, can we do this for the kind of problems we want to solve that would lead to the outages like I was showing you on the previous slide? So one of the exciting things in formal methods today is that there are numerous instances of successful applications of automated reasoning on large problem instances that arise from the real world. In fact, I would say that the intersection of theory with practice is an excellent driver for research. And in my talk today, I'm going to especially highlight the domain insights that have driven my research in this space. Because all of the details you can find in the papers, but I hope, and that's part of what I was discussing with Professor Wright, I really want to share with you some of the key takeaway lessons as we have worked to create formal verifiers to solve the kind of problems we want to in this space. Any questions so far? Actually, I'd like to keep this interactive. So if there's any part that you have a basic question about, please feel free to ask me. I'll be very happy to talk about that. So our approach at a very high level is that we want to take inputs, protocols, and configurations, and we do want to consider all possible forwarding tables and all possible packets, and we want to find bugs if there are any violations, or be able to say with confidence that we have a proof that the network is correct. In particular, the approach that I'm going to use can be viewed as a three-step process. In the first step, we're going to construct a formal network model of the behavior that we want to capture. In the second, we will try and formalize the property, the correctness specification that we want to check for that network. And both of these we will write in, express as formulas in first order theories. I will tell you in a second what I mean by that. But really, the important thing is that we are going to express them both in terms of a formal language of formulas so that their meaning is unambiguous. It's very precise, it's unambiguous, it's something we can reason about mathematically, because natural language specifications that you might see in a documentation manual or something could be ambiguous. And what we're going to do after we've created these formulas, we are going to give them to an engine called an SMT solver. I will tell you again in a second what an SMT solver does, but really it's the SMT solver that is going to be doing the hard work of searching for a bug or searching for a proof, but that's what we'd want to utilize. So what is an SMT solver? You might have seen logic, or you might have at least looked at Boolean logic, propositional logic. Essentially, you can think of this as using Boolean combinators like not, conjunction, disjunction, implication, maybe some quantifiers if you like, on expressions that come from specialized theories. We often call these first order theories because they have special meanings to the symbols. So examples of this is like, this might be an uninterpreted function f This might be an expression in bit vectors, where we are using, for example, the C operator for right shift and a bitwise AND operation here and so on. This is like a formula in linear integer arithmetic where the X and the Z are integer values, and we can use constants, we can use the plus operation and the less than with the usual arithmetic meaning. And we often in software also find useful to use array expressions because we want to talk about memory, we want to talk about arrays and so on. So these are expressions in first order theories, and we can combine them in different ways in order to create first order logic formulas that we will interpret with the semantics of the theory. And this kind of formula we can give to an engine called an SMT solver. SMT stands for satisfiability modulo theories, where we are checking whether there exists any assignment of variables such that the formula is true. And if we find it, then the formula is satisfiable and the SAT solver can give us back such an assignment. In case no such assignment exists, the SAT-SMT solver can also prove that no such assignment exists, and many proof generating solvers can even give you a proof in some kind of form that you can check. So that's the important thing, that we can either find a satisfying solution or we know that we have a guarantee that no such solution exists. And there are many modern SMT solvers that have made tremendous advancements in the last decade or two based on actually advancements made in Boolean satisfiability, or what are called SAT solvers. And these technologies and tools have become so advanced and so powerful that they can handle large problem instances, even though the theoretic complexity of these procedures is very high. But what's interesting is, again, as I was mentioning, that in this field, the intersection of theory and practice is such that many large instances are solvable by these solvers, using many of the theories that are useful for reasoning about programs and systems, like equality logic, bit vectors, linear integer arithmetic, arrays, and so on. So this was just setting up some background. That's going to be our game plan, right? First order logic formulas in these kind of theories that are supported by an SMT solver. And hopefully we can formulate the problem in such a way so that by checking whether a formula is satisfiable or not, we can get some information about the correctness property we are interested in. Okay, is that part okay with everyone? Any questions so far? Good. Yep.
Is the idea what the first order logic formulas, they're supposed to describe how the network is, and the theories are the conditions that you want to satisfy?
So the theories, you can think of theories as just specifying the grammars in which you can write the formulas. Okay, so they allow certain symbols. So these are the usual logical symbols and some quantification symbols, but these are symbols like, the plus is the usual plus that we expect in arithmetic, and so on. So think of this as just specifying grammars that you can use in the expressions which you use to create the formulas. Okay? Yeah. Other questions? Yeah?
Yeah, when you say set solvers can handle large formulas, is that the number of clauses, or is that the number of Boolean variables, or
both? They can easily solve. So again, I'm not talking about random SAT problems, right? Because those we know, even with small formulas, can be arbitrarily complex and hard. And there's that usual phase transition based work, which tells you for random SAT problems, even the best SAT solvers can die. But for formulas that arise in practice from real designs, from real programs, from real systems, there's often so much structure in there that the modern SAT solvers, their heuristics and their ways of learning have become very good, that regularly they can solve, at least for SAT solver, problems with millions of variables. And it used to be just 20 to 25 years ago of the order of hundreds. So there's been 2 to 3 orders, maybe more magnitude improvement in the capacity of these solvers, which is what has made things very interesting. Because now some real world instance problems are within reach of these solvers. If it weren't the case, yeah, we would still be doing old style theory, informal methods. But really what I'm here to speak about and what I'm excited most about is the intersection of theory with practice. Other questions? Okay. So let me also just give one slide view of the kind of properties that we will try and target. So these are, things like reachability. In a data center network, you may want to check whether this pod, this node can reach this node. So that's often something that data center designers want to ensure for all of the top of rack switches, which might be sitting at the bottom here. You may also want to check for things like no transit. If you're having a customer, a provider send you some traffic, you don't want to advertise internally because of the business relationships. So you may have some kind of a property that you want to check, which is a no transit property. Often you may want to make some logic in the configurations. So you want to check whether you have equivalence of what you had before and what you have after. So that's router or subnet equivalence. Certainly one property is that there should not be any routing loops. And that's one that's often ensured with the design of some of these protocols, but also something that you might check if you inadvertently make a mistake. Things like no black holes is you certainly don't want traffic to get mysteriously just dropped without you even knowing that that traffic got dropped. So these are the typical kind of properties we aim to check. Of course, the big question is, how am I going to construct such a logic-based model for the network control plane? And this is the work that we did almost more than 5 years ago now, but this is described in this work in the project we called Minesweeper. So in Minesweeper, what we started with was there was a lot of rich literature in the networking community on what a generic distributed routing protocol looks like. And there was a lot of work done on routing algebras. Let me just take you through a little bit of that as the motivation for the way we came up with in order to do a logic-based model. So in a typical generic distributed routing protocol, the origin, which is a single destination here, creates an initial announcement stating that it has a path to D, to itself in this case. And here I'm going to actually describe what happens in an idealized RIP protocol, which is the routing information protocol. It's just a very simple, one of the basic routing protocols. So the origin first creates an initial announcement stating that it has a path to destination D. Let's say that its path is of length 0. So that's what it will advertise. It will advertise to both of its neighbors. And the neighbors that receive the announcement pass it on to their neighbors, passively modifying it. Okay? And I'll tell you in a little bit what kind of modifications are done with different protocols. But in any generic protocol, that's one step where the person who receives it, the router that receives it, is going to modify it and send it on to the other neighbors. Nodes that get multiple announcements, like this node 2 here, when they receive multiple announcements, they choose a best one based on some criteria. And that criteria might be different for the different protocols, but ultimately it's going to choose a best one among the announcements that it sees. And finally, if the protocol, so in this case, let's say that 2 chose to keep the announcement from 1. And in this case, this is what our current state looks like, where each maybe you're not getting the one in the camera, but okay, we got them all back. Good. So 2 might have just chosen the one from 1, and I'm not saying yet how it chose that, but let's say it had some criteria. And eventually, if the protocol is well designed, hopefully the system converges to a stable solution, by which I mean all nodes are happy. They don't switch their choice anymore. So they can be locally happy if they've chosen the best, and that best choice doesn't change, even if the neighbors continue to send their announcements to you. So this led to more work by Griffin and al., where they said, okay, they're going to use this generic view of a distributed routing protocol, and from a imperative stateful program that might describe how these updates happen, one can think of extracting a logic-based model. The essential things in the logic-based model are you must capture the choices of the paths at every node U. You must also have some way of expressing what is going to be the best value chosen at node U, and then assign that to the path that will be chosen. So the path that node U will pick will be the best among the choices it has from all of its neighbors. Okay, so that was the essential idea, and they called this the stable paths problem in order to reason about convergence of protocols. Because if they are able to find a solution to this, then the protocol is guaranteed to converge. And then they identified conditions under which you can have such convergence and so on. But the main idea that we took away from it is that each node is locally stable at the point where there is a solution. Okay? And Griffin and all used this SPP work, shortest stable paths problem, only for reasoning about convergence of protocols, but we used it now to analyze configurations. So how are we going to do it? One common theme whenever we use automated reasoning is that starting from programs and systems, we build formulas which we hope to give to SAT and SMT solvers that, as I was just saying, have become wonderful at capturing and solving large instances. So for us, the domain insight for capturing the control plane behavior was that network routing protocols are designed to generate stable paths. That is, the routers keep exchanging messages to make the best local choice, which at some point becomes stable. Okay, so that's what we are going to do. Our idea was that we would capture network control behavior in terms of logical constraints or formulas, such that satisfying solutions of those constraints or of those formulas are stable paths in the network. And this was something which people before us had really not thought of doing at all. They were actually modeling the exchanges of messages with each other, and so that led to a lot of extra work they were doing, as it turns out. So here I want to highlight some of the key design choices that we made in Minesweeper. So choice number one was that we decided to model routing graphs, not individual routing paths. And the reason is that in data plane, the reasoning can be done per packet, per path that a packet takes, because there is no interference between packets along the different paths. But in the control plane, routing messages along different paths interact with each other. And modeling that interaction actually can be quite expensive. So we said, how about let's not really look at paths, but look at the complete graph. So our domain insight was that all the stable paths that emerge share the same graph. So that's why the satisfying solutions that we want should not just express the stable paths individually, but should really represent the stable routing tree in the graph. And in many cases, when you allow multipaths for a single destination, it really means that it can also result in a rooted acyclic graph for multipaths. So that was our choice number one, that we didn't want to model individual paths, but we wanted to model graphs, all in the same query. The second choice was to not compute any intermediate states due to exchange of routing messages, because again, this could be very expensive. And indeed, we found that network practitioners are often interested in properties over the stable states after the protocol is converged, because they were, okay with figuring that there will be some transient states where the properties may not hold, but they at least want to ensure once the protocol is converged, that the stable states satisfy some property. So our domain insight was that the transient states matter for some kinds of things, but less than the stable states. There are still a large class of properties that they are very interested in checking on the stable states. So that was the design choice we made, that we were not going to compute intermediate states at all, but we were going to perform a search on the final stable states. And this often scales much better than iteratively computing the sets of states that occur in the middle. Okay, so this was again quite a departure from all previous efforts done in this space. I'm sorry, I may or may not have time, but I'll be glad to tell you more about related work in this space. But that was one of the novel things in Minesweeper. And it was very much due to the domain insights that we had and talking with network practitioners that we decided to model things this way. So more formally, we use what's called a stable routing paths SRP model. And mathematically, it's a 5-tuple. We have a topology with a distinguished node, which is the destination. So it's the usual graph with a set of vertices that express, that represent routers, the edges between them that represents the network topology, and a distinguished node, which is a particular destination that we are reasoning about. We, in order to model generically any kind of protocol, we allow ourselves a set of attributes. Think of these as the routing message fields. Could be integers, could be AS path length, could be anything that you want. A new protocol, you just design it, you can create some routing field announcements in it. So that's what we use to model this. And there's another distinguished symbol bottom, which represents absence of a route announcement. So if you don't have any route, then we will treat this as bottom here. So it's extended with that. We have a preference relation, which is over the A cross A, which determines the best route. Given 2 routes, it will select the best one. We have a transfer function, which over an edge can modify a route to either drop it or modify it in some way. So again, it's just a transfer function along an edge in how the router or different protocols can modify a route announcement. And we will have an initial value at the destination, which is the initial message at D. And often these things are determined by a particular protocol, but these can also get affected for a specific protocol, per router set up in their configuration. So that's how we decided to create a model that is going to work on the configurations for the protocols. Yeah.
So I have a question regarding the transfer function.
Yeah.
So it's a message applied on a particular edge in the routing graph.
Yes.
So you just told us that you don't worry too much about the transient states, but this transfer function will give you a transient state.
Right. But we are not going to do any reasoning over that transient state.
Okay.
I will show you in a second how we model the constraints so that the solutions will only capture the states.
Okay.
But we have to actually model what each edge does.
Sure.
When the routing announcement is sent from one router to another, obviously we must model how it's modified.
Okay.
So this is what is captured by the transfer function in the model. Yeah, good question. And actually there are many network protocols. I'm sorry, I don't even know how each of these operate, but my collaborators do. But, there's a virtual acronym of, for many of these, and there's like a zoo of, I feel like, acronyms for different kinds of protocols. The important thing for me is that Minesweeper handled them uniformly in terms of this theoretical model on stable routing paths model. And again, I'd like to point out, a key takeaway is that it's due to the generality of our logic theoretic models that we can model any protocol and model them uniformly so that we can even talk about nice nifty features like route distribution, redistribution from one protocol to another using because it's in the uniform model for us. And we will now talk about a solution for an SRP model. It's a labeling from nodes to attributes, including not having any route. So it's extended with the bottom symbol here. And the important thing is that an SRP solution must be locally stable. So each node chooses the best among the routes transferred by its neighbors. And at the point where that choice doesn't change anymore, we will say that it has locally stabilized. So let me just first give you an example of the same RIP protocol that I had shown you as a generic protocol. Here, the set of attributes is just a set of natural numbers 0 through 15. It's because RIP just drops everything if the path length becomes more than 15. The preference relation for this is the usual less than over the natural numbers. The transfer function is drop the route if A is already 15, right? So if the announcement that you get already has 15, I'm going to drop that. But otherwise, I'm going to add 1 to it and send it to my neighbor. Initial value at the destination node, of course, is 0 because I have a 0 length path to the destination at the destination node. So this is just an example of an SRP model, how it can model RIP for you. So now our game plan was that we will do SMT-based verification. So if we want to check, does property P hold in the network, we're going to first create a network encoding formula where the network is modeled as an SRP, and let me call this formula N. And I'm going to AND it, this is a big AND, with the negation of the property. And then I'm going to give this to an SMT software. Okay, so let me also give you a little bit of detail of how we get this encoding. So here is a small example of 3 routers connected with some external network, and let's say we were going to reason about some property on this. So what we need are variables that represent the stable route selected by node N. So for each node, we are going to have these A variables. We are going to also have these extra variables X and Y on every edge. And these are going to, so for each node, the kind of attributes we have would be things like whether this route is valid, what the prefix it is for, the prefix length, administrative distance, all kinds of other field announcements that we found useful for modeling protocols used in practice, such as RIP, OSPF, HTTP, and so on. And here I'm going to again use the SMT theories that are well supported by Z3 and other SMT solvers called bit vectors, integer difference logic, and so on. So we have these variables. We are going to now add constraints. We are going to say that export is equal to the export policy applied to the nodes R3 solution. Right? So that's the additional constraint. This is part of the transfer function that happens. And Y4 is going to be the import policy of R2 applied to what we get from here. And the third kind of constraint I'm going to add is that AR2 is actually going to be equal to the best among the choices that it has, which is Y1, Y4, and Y5 only. Right? So this constraint is what's going to enforce that whatever solutions I get by doing transfers will ultimately still satisfy my stability condition. To answer your question, Ron. So I'm not modeling, I'm modeling their values, but I'm not really computing them. And I'm not going to even check them. I'm only going to check ultimately the stable solutions. So I do want to point out that note that these variables A, X, Y are symbolic variables. So they are allowed to take any possible value, which means that we are implicitly modeling all stable solutions. Yeah.
Something I'm just unclear about.
Yeah.
The progression of these protocols, steps.
Yes.
Multiple rounds of steps. I'm having trouble seeing how you're doing the progression. I just modeled the final state. How do you know you can get them?
That's a good question. And in some sense, it's an approximation. And in most practical cases, you would be able to get to the final state solution. If you are interested in, do I converge or not? Do I get to a stable solution or not? We are not answering that question. We are saying, if you do converge, then it will have this kind of property. Let it show that this node is reachable from there. Yeah, good question. And that was the reason I went into those domain insights. We decided not to model these intermediate states that are when you are doing the progression. We are saying, actually, for practitioners, the final states that you reach is really what will determine what forwarding tables are put on the database. So we are very interested in seeing what actually gets sent at runtime due to these forwarding tables that emerge from the converged states. But we are not limiting them to given forwarding information. We are deriving it in some sense implicitly from the configurations. Yeah.
Why do the X's and Y's have to be separate variables?
Great question. Actually, if there's nothing going on in these, we do an optimization where we make them equal. We will use a single copy. The paper describes tons of simplifications that we ended up having to do, but in principle, I wanted to show you that this message here could be different from this message here because of the import and the export policies. So we allow all possible such values to be taken. Yeah, good question. Any other questions? Great. So now, if we have a property like can router R1 reach some host H1, we can also define, so we have defined, the paper will describe details, predicates like there's a can reach on the control part, and then there's a forwards, which really means that on the data plane, you have a forwarding table that says forward from here to there because of having a control route. This takes into account the access control lists, which even though a route might exist, might drop the packets. So we take that also into account, and now we can have a property also expressed in the same kind of basic language that we've created over here. And now we will give the conjunction of this network formula, which is capturing the stable states, and the negation of the property given to a SAT solver. If the SMT solver, says that the formula is satisfiable, it means there exists an assignment to all those variables such that the property is violated. So now we get our bug. We actually get a stable solution which also shows the property is violated. What if the SMT solver says it's unsatisfiable? The formula, there's no assignment of variable that will make the formula true. It means either there is no stable solution here, or the property holds on all possible stable solutions. So that's really what we were after. And then again, in practical examples, we just assume that there will be a stable solution, or we can check it separately for some given route announcements. I can take that question offline, but in most cases, we are not looking for, oh, there is no stable solution. But what we are checking is, even if there are multiple stable solutions, we would have checked all of them. Yeah.
So here, there can be multiple stable solutions, but if you actually let the routing protocol starting from each state and run through the progression, you may end up with one of the states, right? So in other words, when you say the property is holds on all possible stable solutions, maybe in practice on some stable solutions the property doesn't hold, but even on the one that shows up in practice it holds, right? That's situation. Is it possible?
It is possible, but for us, we will actually show you that violation, even if that doesn't happen very often, because we are capturing all possible stable solutions.
Right. So my question is, so the formula, right?
Mhm.
This method you get like basically you read about all possible stable solutions, right? But maybe in practice only like a small subset shows up all the time.
Right.
The other ones never show up because the implementation dictates that.
Sure,
And
agreed.
in that case, you say the property,
Is violated
right?
on something which doesn't show up often. In my opinion, it's the job of the designer then to say, okay, it is an alarm, but I'm not going to worry about it because this doesn't often happen.
So it's a false positive. It often can happen, but you know the implementers they can use their judgment to rule it out.
Exactly, exactly. But more often, they are worried about multiple solutions, but they're testing only checking one of them.
Mhm. Do you know if the in practice is it frequent to have those like small subset scenarios that show up, but now the theoretical stable solution, the other ones show up?
It doesn't happen very often. For us, it didn't. Any of the examples bugs that we found were true real bugs. Yeah.
All right, cool.
Yeah.
So unsatisfiable, how do you know, I mean, do these solvers possibly return determine whether it's satisfiable or unsatisfiable? You're just saying that doesn't happen very often in practice?
No, they are returning unsatisfiable or satisfiable. So if there is any solution, they will say satisfiable and give you that solution. And only in case there's no satisfying solution will they say it's unsatisfiable.
Doesn't that solve reset?
Yeah, it does. I mean, it will, but it's it's NP complete or worse, because here we're not even talking just that, but theories with integer arithmetic and so on could be.
There can be
Yeah.
timeouts as well, right?
Yes,
There's-
of course. That's always the case. And my job is to try and avoid those as far as possible. And I'm going to talk about it. I don't know how much time we have since we started late.
Yeah, so, can you wrap it up in about 5 minutes?
5 minutes?
People can
Okay.
Stay if they want after that.
Okay, let me try and actually get to the more interesting part, which is what happens when there are timeouts, right? Because there is a problem of scale. So let me just say that really we are checking all possible forwarding tables that might emerge from the given configurations and for all packets. And the tool itself, which is publicly available, actually did a lot of work in capturing many properties of the networks and many design features of the networks and many properties that it can check based on a tool called Batfish for the front end, which actually processes many vendor-specific configurations and so on. It does not support convergence, does not support quantitative properties, and checking multiple destinations is expensive. Just a disclaimer, I'll be glad to tell you more. So these are just some experiments that the results for which I'm showing you on 152 legacy networks that have been extensively tested, but we actually found bugs in them after using this approach. And they had anywhere from 1 to 23,000 lines of configuration code that we processed, created a model for it. Of course, the paper will describe a lot of additional optimizations and simplifications we needed to do. But in the end, under 1 second, we managed to find violations for many of these legacy networks. And then when we did some scalability experiments on some data center topologies, which are parametric, let's say the number of pods and so on, we were able to find for many properties of interest. And in the interest of time, let me not tell you what each of these are, but I'll be glad to stay back and tell you more. We were able to scale it up to roughly 400 to 500 routers, right? But there's a problem of scale here. The time grows exponentially with the number of routers. And industrial data centers have 1,000, 5,000, even 10,000 routers today and growing. So what are we going to do? And so one of the things we did was exploited the symmetry that exists in the topology of these networks. And we were able to show some abstractions based on symmetry, which preserved some of the properties. And by this, we were able to scale it. But often in practice, the topological symmetry may not exist outside of data centers, or the policy may break the symmetry. So what if there's none? Another thing that we tried was use the classical work on abstract interpretation, where we abstracted the announcement fields. And this also was able to give us a big performance boost. So what we have here is the time for simulation, varying by data center size, and the time that it takes, and the concrete network without any abstraction takes a long time. You see that exponential kind of curve, but with abstraction, actually we were able to keep it down a lot. But it still didn't scale to 5,000 routers. And these are described in the papers that I have mentioned over here, which I'll be glad to tell you more about. And there were many efforts by others also done in order to improve the situation. Which brings me to the part that I will try and wrap up within 3 minutes. It's again using abstraction, and it's described in some real work that was published last year. So the question we asked ourselves is, okay, let's take a step back. We have this big, huge formula, rich in detail, captures many of the network design features. How can we do abstraction more systematically? And one of the things that we saw was that verifying certain properties, for example, reachability, actually may not need to identify the best route available. In fact, network administrators often want to have backup routes to best routes, because a link could fail, a node could fail. So often they are, if they don't want some routes taken, they explicitly prohibit them by using route filters. So one of the decisions we made was we will continue to precisely model the route filters. We won't extract them away. We'll keep them. But we can throw away the route selection logic. In fact, for policy-rich protocols like BGP, this can often involve many variables, many constraints, and in most cases, we might even be able to just abstract it away. So we call this the non-deterministic routing choice, or NRC abstraction, where the idea was that each router non-deterministically, which means just randomly, picks one of the routes received. It must be an available route, not necessarily the best that is chosen, but any chosen route must be compliant with policy. And now we have an abstraction N prime that has many more behaviors than the real network would have, because it's got the best route plus many more. But if we are able to, we at least can get sound verification, because if we say that that is correct, we know that the original was correct. But if it isn't, then we may have some work to do, and we actually created a hierarchy of abstractions with refinement if there are false alarms, which we can also check using standard techniques. So again, some of the key takeaways from this work: non-deterministic choices is often a very good way of getting sound and useful abstractions. Furthermore, if you have technology like model checkers or SMT solvers, if you get counterexamples, and once you determine that they are spurious, as in they are false alarms, they're not real, then you can use them for doing refinements. And so that is the work that we did. We created a different verifier that does this NRC abstraction and actually does an encoding to two different solvers. This solver has specialized support for graphs, which was one of the domain insights. We wanted to model graphs, not just paths. And this provides things like a reachability predicate, and all of the benchmarks are publicly available too. I'll skip the details, which again, I can stay back and tell you about it. But what we wanted to check was on a parametric example with what's called a valley-free property, which means that paths should always go like an upturned valley. They shouldn't go up and down within a path. So that kind of policy can be implemented using community tags in BGP. And here is the real graph that I really wanted to show you, which is showing the number of nodes in FAT3, because it was a synthetic benchmark. We could create any size FAT3, has a very structured topology. And what we were able to show is that in a 1 hour time limit, we were actually able to check reachability using one of those solvers right up to more than 35,000 nodes. So I was super happy, because trying to get 1 or 2 orders of magnitude improvement in scale doesn't come by along often. But when it happens, it really, again, gives a big jump to the kind of things you can handle in the real world. So I'll just say that the abstract settings we found were uniformly better than concrete settings. You can see those graphs here. We are plotting time against the size. The blue ones are for the monosat solver with and without abstraction. The red and orange are for C3 with and without abstraction. And in all cases, the abstraction really helped with both solvers. And also we got actually no false alarms in these data center benchmarks. We did get some false alarms with some other WAN benchmarks that we had played with, where we used the refinement strategy. But the thing I was most excited about was that we were able to push the verification. I mean, granted, there's some disclaimer here, right? It's a synthetic benchmark. It's not quite the actual configuration, but we did try to model the real world policy, and we were able to push it to showing complete verification for these. So just wrapping up, some of the lessons learned. Build the logic-based model first, leverage domain structure, modeling the network control plane's stable behavior. enabled us to directly use SMT solver technology. Don't abstract too early, because the logic-based model we started with is rich in detail. We wanted to model the route filters, we continue to model them. And these features are considered important by network practitioners. After you have that, then you can utilize all of the things you know about logic-based abstractions, compositional methods, abstraction refinement, in fact, your favorite method on top of this. We went ahead and used many of our favorite methods on top of the SRP model. So I mentioned briefly the use of symmetry abstraction, use of abstract interpretation, and we also, others did work with failure analysis and put it in a programmable platform. I didn't get a chance to describe, I did talk about ACORN, which is this NRC abstraction. I didn't get a chance to talk about compositional methods, modular methods, but we use those also, where we separate the big network into smaller components and talk about their interfaces and do compositional reasoning. So let me end there. In all of the work, we aim for soundness, generality through symbolic reasoning, and scalability. I do want to thank my collaborators, Ryan, Ratul, Divya, Tim, and Dave. And I'll just leave you with this final summary of most of what I described in my talk, and I'll take questions. Thank you.
Great. Thank you so much. Please join me in thanking Professor Gupta. I think in the interest of time and this wonderful reception we have laid out for you, let's do the questions informally over the reception. For those of you on Zoom, sorry.
I can stay back and answer questions on Zoom.
Very good. Okay, so we can keep the
Yes.
Zoom open as well.
For a little
And
bit.
then if any of you need to leave, feel free to leave, but happy to, I think Professor Gupta is happy to entertain the questions, but we'll do it over food and drinks as well. So thank you again.
Thank you very much.
And before I close out the Zoom, any questions on the Zoom, feel free to raise a hand or drop it in the chat. All right, seeing none, thank you for joining on Zoom as well.